Welcome folks. In this video we are going to look at questions from section B of science paper 1 for the year 2023, and we'll consider this video as part 2, where we are going to begin from question 4. So let's dive right in. So we have figure B4.1 shows a crane at a construction site raising a steel block of mass 100 kg through a vertical height of 16 meters in 20 seconds. So from the data we can see that we have mass of the steel block, and we have the vertical height which is 16 meters, and the time elapsed was 20 seconds. Now let's have the first question. So calculate the work done by the crane. So let's look at the formula. So we know that work done is equal to force multiplied by distance. Now if we look at the work that was done here, this work was done against what? Gravity. Why do we say so? Because the steel block was moving in this direction, so it was moving in this direction. So how can we calculate the work done whenever we are looking at against gravity? So let's see what we can do here. So from the data we have the mass. Now let's look at the force. So force is equal to mass times acceleration. So that is the force if you look at the second law of motion for Newton's. Then so since it's against gravity, where there is A we can put where there is A we can just put G for gravity, since we are looking at the force against gravity. So let's substitute where there is F, we put mg. So the formula now becomes mg. Now for D, we know that D we are just going to put h, since we are looking at the height, so it's h. So you can see that whenever you are looking at the work done against gravity, the formula for work done is just the same as the formula for potential energy. So that's what I wanted us to look at. So let's now find the answer. So the mass is 100 kg times gravity is 10, then the height is this number 16 meters. So we have our 16 meters here. Now we do the mathematics. So 100 times 10 times 16, so I'm getting 16,000 so joules. This is our work done by the crane. Now we move on to Roman number 2, power developed by the crane. So power is given by this formula, where we need to find a coefficient, quotient of work done by the time taken. So remember, the work done we have calculated is 16,000 over then time we were given the time is 20 seconds. So whenever you have the work done divided by the power, you get, divided by the time, you get the power. So 16,000 divided by 20 will give us 800 watts. So this is our power for this question. Now let's move on to B. Given that the total power which is the power input to the motor is 1000 watts, calculate the efficiency of the crane. So say efficiency is equal to, say, power output over power input. Then multiply by 100%. So the power output is this one that we've calculated. So make sure that as you are making these kind of calculations, make sure that the power output should be less than the power input. So 1000 is greater than 800. So if we do the mathematics here, we'll be able to get the efficiency less than 100. We need efficiency less than 100. So if we say 800 divided by 1000, I'm getting 0.8. So 0.8 multiplied by 1000, I mean 100, this will give us 80% as our efficiency. So this is how we can answer this question. Okay, so we move on to question 5. Figure B5.1 is a graph showing the variation of temperature, degrees Celsius, with time second when frozen water is heated for some time. So the whole thing is starting from the frozen water, which is ice. So we are looking at ice. Remember, ice is just water in solid state. Now, what happens if this ice is heated to a certain temperature? We are going to have a liquid water. So by what process can we change a solid into a liquid? We have what we call the melting. Now let's now analyze the whole thing. So we can see that here we have the temperature of 0. So the graph is like this. So there was a certain process that was taking place at this point, then at this. So this is like the initial of that process, then this is the final. The final means that the process is completely done. Then from there we have now this line here, which is indicating a certain solid state. Then we have another process taking place at this point. Now let's go to question A. What physical change was happening to the water at a point labeled A? So what physical change, what process was taking place? Now remember, we are dealing with ice. So the process that was taking place at A is just the melting, because we are looking at the change of a solid into a liquid. So we have melting. In which state is the water at the point between A and B? So at this one, we are just going to have a liquid, since the solid ice has melted into a liquid. So here we have a liquid. Okay, so now for question C. When the temperature starts to rise, the volume initially decreases and then increases. So state the reason for this observation. So now let's see if we can analyze the whole thing. And I'm sure you've once at least observed that ice floats on water. Why do ice floats on water? So the reason being is that ice is less denser than the actual liquid water. Now what happens when ice is changing into a liquid water? So we are saying that there will be an increase in mass. So since the mass is increasing, then the volume, the size would decrease. So that's what happens. That's what we are trying to look at here. So the whole thing is about what happens in terms of the volume when a substance is changing from a solid into a liquid. So we are looking at when the temperature starts to rise, the volume initially decreases and then increases. So we'll say when a solid ice starts to melt, the mass will increase. The mass will increase, whereas the volume the volume will decrease. So the volume will decrease. So that is the first one. Then we are told, and then increases. So the increase now will come after that water. If that water is heated, it will gain the kinetic energy, and that energy will cause now the water to expand. So the continuing of temperature increment will cause the substance to expand. So to expand, thus a rise in volume. So that's what we are trying to look at here. So we have the first one, the volume will decrease due to the change from solid to liquid. Then after that, whenever the water is continued to be heated, then we are going to have the expansion, which will now increase the volume. So that's what we can say for that. Okay, so now we have question 6. Figure B6.1 shows a ray of light traveling from a glass to air at an angle. The refractive index of glass is 1.52. Okay, so we have been given the ray of light. So this is our incident ray. Then we have the angle of incident at this point. Then this is our angle of refraction. Now let's look at the first question. So the first question is just define critical angle. So what is critical angle? So critical angle is just the angle of incidence when the angle of refraction is equal to 90. Okay, so that is how we can, that's in terms of the simpler definition that we can give for critical angle. So remember, whenever the angle of refraction is equal to 90 degrees, then the angle of incidence that we have is the critical angle. Now let's look at question B. So under question B is calculate the critical angle. Now remember, we have been given the refractive index, which is 1.52. So how can we use the refractive index of a given medium to find the critical angle? So the formula is refractive index is 1 divided by sine critical angle. So where there is any, we put the refractive index, which is 1.52, 1 over sine IC. So over 1, we cross multiply. So we are going to get 1.52 sine IC is equal to 1. So this is just the same as we are going to find the arc inverse of the quotient of 1 over 1.52. So sine IC represents the critical angle. So what is 1 divided by 1.52? So according to my calculator, I'm getting 0.657894736. Then what you do, we know that we need to shift So we have IC is equal to sine of this 0.6. So shift then sine answer. So I'm getting 41.1 degrees as our critical angle. Then we move on to question C. State two conditions for total internal reflection to occur. Total internal reflection is, let's say we have, this is a glass or maybe water, then here we have the medium air. So medium air, let's say this is medium 1, this is medium 2. So what happens when light is moving from a more denser medium into a less denser medium? So in terms of the bending, we are expecting to have the refraction away from the normal. So if this is our normal ray, then the bending will be away from the normal. Then if we move this incident ray, maybe we take it to a certain position like this one, we are going to have the critical angle. Remember, the critical angle is when the angle of refraction is equal to 90. So the angle that we have formed here is the critical angle. Now what happens if we shift this line past the critical angle? If maybe we put it to this position, so instead of refraction, this time we are going to have reflection. Instead of bending, then the light will just bounce back. So this is what we call the total internal reflection. So now the first condition that you need to look at for total internal reflection is that for this to occur, in terms of light must travel from a more denser medium into a less denser medium. So that is the first. So the opposite, according to science, will not take place. If light moves from air into a glass or into a more denser medium, total internal reflection cannot occur. But the reverse can give us the total internal reflection. So we'll say light must move from the more denser medium to a less denser medium. So that is what we can give as our first condition. Then the second condition, for us to achieve the total internal reflection, the angle of incidence must always be greater than the critical angle. Then D, give one application or use for total internal reflection. So they are used, we can say, in binoculars or periscope. So you're just looking at the instruments that we can use to view certain object over a distance. Okay, so now we move on to question 7. So B, figure B 7.1 shows an AC generator with its main components labeled A and B. Okay, now let's look at the first question. Write down the names of components C, A and B. So let's look at our A. So A, let me see if I can help you to remember the difference between the AC and the DC. You may find one may have this rings may have some gaps, but for this one we can see that it's just a continuous one. There are no gaps here. So the one with no gaps is called slip rings. Then whenever you see these gaps here, this is what we call a split. So that's the difference. So for the other generator, it has the split ring commutator. So the split, whenever you see a gap here, it's a split. When there is no gap, then it is a slip rings. Then for B, these are just brushes. Then for B, state 3 factors that increase the magnitude of the electromotive force, EMF, produced by the generator. So for us to produce this EMF, this coil must rotate. So we can rotate it in this direction or in whatever direction, but let's not focus on the direction, but we need to rotate this. Now, let's say if we want to produce current with a greater value, or voltage with a greater value, what are we supposed to do in terms of rotation? So the size of rotation, the force that we are applying, how fast the coil is rotating, will determine the amount of EMF produced. So the first factor that we are looking at here is how fast the coil is rotating. For example, maybe you've seen there are those bicycles that have this type of generator. So when a person paddles the paddle very fast, the more he or she paddles it very fast, the higher you see the brightness on the torch. So that's the key point. So the faster you move the coil, the greater the EMF. So that's what I wanted us to look at here. So we'll say by increasing the movement of the coil. Okay, then for number 2, the second factor, we can say by using. So by using strong magnets. So the strength of a magnet also matters. So the weak magnet will give you weak electromagnetic force. Then the other one, by increasing turns on the coil. Okay, so these are some of the factors that we can look at here. Number 8, figure B8.1 shows an electric circuit with a 5 ohms resistor R connected to a 12 volts supply. Okay, so the first one, state Ohm's law. So we can say Ohm's law states that current through a conductor is directly proportional to the voltage provided all conditions remains constant. So the conditions, an example of the conditions that we want to remain constant X is like temperature. Then for B1, calculate the reading of the instrument, labeled A. So let's go back to our A. So A is just the ammeter. So what is the function of the ammeter? Ammeter measures current. So this is same as we need to calculate the current. So we know that current is equal to voltage divided by resistor. What's our voltage? So our voltage is 12 volts here. Resistor, we only have one, which is 5 ohms. So we have 5 ohms. So 12 divided by 5, we get 2.4 amps. So this is our current. Then for V is just the voltage. So what voltage is at this point here? So voltage, we just get the same. So we just say voltage is equal to 12 volts. Why? Because we only have one resistor and the connection is in series. So the same amount of voltage that was produced by the source was the same amount of voltage that was being consumed. Or if we want, we can also find the same answer. We can see that voltage is equal to current times resistor. Remember, the current is 2.4, resistor is 5. So if you multiply 2.4 times 5, you still get the same answer, 12 watts. So this is what we can do. Then for Roman number 2, what is the cost of using resistor R for 6 hours a day for 30 days if power costs 15 ingwe per kilowatts? So we need to find the first power. So what's power? Power is equal to voltage times current. So remember, what's our voltage? 12 volts. Current 2.4. So what is 12 times 2.4? We get 28.8. This is our power in watts. Now remember, whenever you are dealing with cost, you need to convert your power in watts into kilowatts. So what you do, we know 1 kilowatt is equal to 1000 watts. So to convert from kilo to watts, you multiply by 1000. Then the reverse, you divide by 1000. So remember, we are converting from watts into kilos, so we divide by 1000. So my calculator is giving me 0.0288 kilowatts. So now we can go to the formula for cost. So say cost is equal to power in kilowatts times time in hours times cost per unit. Remember, this should be in kwacha. So what's our power? Power is 0.0288 time. Now we need to be careful for time here. That's why we can say that we are given 3 marks, so there is a lot to do here. So we are told for each day 6 hours, but for how many? 30 days. So for 6 multiply by 30 days so that we know the total amount of hours. So say 6 times 30 days, we have 180. So times 180 hours multiply by, now we are given 15 ingwe. So this ingwe should be converted into kwacha. So whenever you are converting ingwe into kwacha, you divide by 100. So 15 divided by 100, you get 0.15. Then if we multiply these 3 numbers, we are able to get our final answer. So 0.0288 times 180 times 0.15. So my calculation, I'm getting this number here, quarter. So let's put K here. So this is our final answer. Okay, now we move on to question 9. Figure B 9.1 shows radiations P, Q, and R passing through an electric field. Okay, so we have this field which is positive here. Then here we have negative. Then identify the emissions P. So P, which radiation must be deflected toward the positive terminal. So for it to be deflected toward the positive terminal, its nature must be negative, because we know that negative is attracted to a positive. So this P must be a radiation with a negative. So between alpha, gamma, and beta, which one is negative? So the negative is beta. Beta has a negative charge. So P is beta radiation. Then for Q, we can see that Q did not deflect, it just went in a straight line. So this means that our Q must be neutral. It's neither positive nor negative, so there was no deflection. So which radiation behaves in such a manner is gamma. So if you look at gamma, gamma radiations have no charge. So if this is gamma, then this is alpha. Alpha has a positive charge, thus its deflection will be a negative terminal. Then give one use of emission Q. One use of emission Q. So one use of gamma, we can say to treat cancer cells. There are so many. Then mention two differences between emissions P and R. P, so P we are saying it's beta, then R it's alpha. So what are the two differences that we can give between beta and alpha? So the first one, we can look at the charge. So we'll say P has a negative charge, whereas R has a positive charge. Then the second one, if you want, we can let's look at in terms of ionizing effect. P has a weak ionizing effect, whereas the R has a strong ionizing effect. Or if you want, we can look at in terms of mass. Alpha has a higher mass compared to beta. The mass is so small. Then if you want, we can also look at the speed. In terms of the speed, beta travel faster than this alpha. Then also in terms of where these radiations can pass through, you can also give into that. So this is the last question for this section B. So that's it for this video. Thanks for watching.